Thank you, Jack, for that introduction, and I want to thank the organizing committee for inviting me to do this keynote. And hopefully you'll enjoy the next 45 minutes. So let's see what I've got here. So what I'm going to do is give you a historical perspective of the first 40 years of Moore's Law. During this time, it was what I call the single-core era, where with every generation, the microprocessor's performance improved. And it was made easy by what's known as NART scaling, and I'll talk about what NART scaling is in a few slides. Well, in 2004, NART scaling ended, but Moore's Law didn't. And that started the multi-core era, and we'll talk about how that happened. And then the next shift was moving from high-power multi-core era to energy-efficient multi-core designs for the cloud, which is where we are today, and which is where my work at Qualcomm is focused. And then I'll talk a little bit about the next era, which is heterogeneous computing with application-specific accelerators. So let's talk about the first 50 years after the invention of the transistor. Since Jack already told you when I got my PhD, I'm also proud to say that I'm older than the transistor, which was invented in the 1950s. And you can see how things progressed. I got this slide from the Computer History Museum, and what they failed to show were two important points in time. The invention of the integrated circuit, which sort of happened almost simultaneously with Bob Noyce at Intel and Jack Kilby at Texas Instruments. And again, I was very lucky to interact with Jack Kilby when I was part of Texas Instruments. So you can see, as things progressed, you start to get more and more transistors on a single chip. And by 2004, about the time when the NART scaling ended, we were at about 500 million transistors on a chip. If you're interested in a longer story about the history of those microprocessors, you can follow that link for a talk I gave at the Computer History Museum. So here's the chart of how we got from 2,300 transistors in 1971 with the 4004, which was the first microprocessor, to over 1 billion transistors in 2005. Now, what is NART scaling? NART was at IBM, and what he observed was that with each process generation, if you can scale all of the parameters of the process technology by a scale factor of k, and k was 1.4, so 1 over 1.4 is 0.7, so the linear dimension was 0.7 of the previous generation. 0.7 squared is a half. So the density of transistors on a chip doubled with every generation. Pretty simple. But the good thing was everything else also scaled. But then after several years of this NART scaling, we got to the point where we couldn't scale everything by that same factor of k. Density continued to improve, but the voltage was sort of flat. And we had other issues. Interconnect became more dominant. And so we could not scale designs as easily as we could. But because there was increasing density with Moore's Law, and Moore's Law became more about new materials, new devices, like we now have FinFETs, et cetera, that we were able to do multi-core designs. And I'll show you how we got performance post-NART scaling. So after NART scaling, we went into the multi-core era. And in this era, single-thread performance improvement was slowing down, and I'll show you some data. But we got performance by increasing the core count. Basically, the cores were roughly similar performance, small improvement in single-thread performance. But because of the density, we were able to put more cores on a single chip. So here's a graph that was put together by Mark Horowitz and some of his students at Stanford. And what you see on the top is, let's see if I can figure out how to work this, that the transistor count increased steadily, but the single-thread performance, as you see, sort of starting somewhere in that 2004-5, started to flatten. Frequency flattened also, Power, and this is a log scale, power crept up very slowly, and the number of cores went up. So this was a plot based on lots of data points, but I can show you some details on the next slide. So here's what I did. I took the last 5 generations of the Intel Xeon processors, starting with Sandy Bridge in 2012, all the way to Skylake, which was announced in July. All of these are 135-watt Xeon processors. So at the same power, you can see that the single-thread performance went up very gradually, slightly. But when you put multiple cores, starting with 8 with Sandy Bridge going to 18, the per-core performance, because we were power-constrained, did not go up that much. Okay? So when you're power-constrained, the per-core performance stays flat. Single core is slightly higher, but you're not going to use an 8-core server processor and run just one thread. So let's look at what happens if you're willing to increase the power. So here I took those same processors, starting with Sandy Bridge, Ivy Bridge, Haswell, Broadwell, and then the last 3 points are Skylake, and took the highest power SKU of those processors. So you can see what happened was initially they were all about 135 watts, and then when it went to Haswell, the power went up to, let's see, which one is the power, the red, 145 watts. It stayed at that with Broadwell, and then as they went to Skylake, the highest performance one was 205 watts. Now notice that the green bar, which is the performance per watt per core, even with higher power, going from the Sandy Bridge from 2012 to last year's Skylake, you can see that actually the performance per watt per core actually coming down, okay? So there's a problem here. So what do? We have to now think about more energy-efficient cores, and that's what I've spent the last 5 years of my life at Qualcomm, trying to get cores that are more energy efficient. And I'm sorry if this is starting to sound a little bit of like a commercial, but I want to share some of the things we did, and there's some science behind this. So if you look at what has happened over the last 4 or 5 years is a lot of companies have started to adopt ARM-based designs. ARM was originally in smartphones, but in the last 2 or 3 years, you start seeing multiple companies building server chips based on the ARM architecture. And what ARM provides is a very clean architecture, and it allows you to do more energy-efficient designs. And I'll show you what we did at Qualcomm. But I like this statement from Peter at ARM, which says, the future requires a new approach to CPU design. And he's absolutely right. So what's happening now? The server industry is moving more and more to the cloud. Public clouds are, with Amazon Web Services, Google, and Microsoft, becoming quite popular. And by 2020, more than 50% of the server processors that are shipped will go into the cloud. So what do we do to meet the needs of the cloud? If you look at the history of computing, there have been disruptions every few years. When I first started graduate school in 1970, all we had was mainframes, and I remember walking with a deck of cards and putting it in a card reader and coming back 6 or 7 hours later with a printout which showed all of the errors I'd made in my program. Then you had to fix those and go back and do it again. Now those mainframes got kind of eaten into by mini computers. Those got eaten into by RISC systems, mainly from Sun Microsystems, and then desktop PCs, then notebook processors, and now it's the era of smartphone processors. What you have to notice is that in all of these transitions, the large systems were replaced by something that was higher volume. Volume economics is what drives the industry. Has for a long time and will continue to do so. And we're taking advantage of this in the designs that we're doing. So let's talk about how things are changing. I spent 12 years of my life at Intel, and we drove the new process technology. And it was driven by the fact that we had a large volume of PC processors that we were building, which justified the investment in the next new node. So if you look at what this shows is in 2008, the volume of PCs was maybe twice as high in the 45 nanometer generation compared to smartphones. But over time, the PC unit volume has kind of flattened or even declining now, and the smartphone volume has taken off. So what you see today is that the investment in new process technologies is driven more by the needs of the smartphone industry and not so much by the PC industry. Now, I work for a company that builds these smartphones, so I have access to a new node before Intel comes out with the new one. So the Skylake that I showed you is in 14 nanometers, whereas the chip that we announced late last year is the first 10 nanometer server chip in the world. So we were able to take advantage of the fact that we have earlier access to the new node. And I'll talk about why the new node is important when you're going for energy efficiency in a few slides. So actually, our first chip, which is shown at the bottom here, it's a 400 millimeter square chip compared to the Skylake, which is a 700 millimeters. So less area because of a more advanced node, and it has 18 billion transistors. Think about that going from 1971, the first 4004, with 2,300 transistors. And what we get with a leading edge node is better performance, better power, and better area. So if you're designing for the cloud, what do you have to do? What's important? It's all about throughput performance. It's not about single thread performance. Thread density, you want to have as many high-performance threads within a certain power envelope. Energy efficiency has to be designed in from day one. So the key metrics that we focused on for energy efficiency is performance per thread, performance per watt, and performance per millimeter squared. Performance per thread gives you the thread density, performance per watt is your energy efficiency, and performance per millimeter square allows you to build these processors at a lower cost and offer them at a very competitive price. So yes, the future does require a new approach to CPU design, and energy efficiency has to go in from day one. So let's talk about data center energy efficiency. So after my 12 years at Intel, I spent almost 6 at Microsoft designing and specifying servers for their cloud infrastructure. If you look at US data centers, they consumed about 70 billion kilowatt hours of electricity in 2014. Data centers are expensive. They cost somewhere between $10 million and $20 million per megawatt in capital investment to build a data center and do the power delivery and the cooling systems before even the first server lands in that data center. So it's a huge capital investment. Energy costs, every watt of server power can cost $1 per year if your energy costs are 10 cents per kilowatt hour. In some places, the energy costs are even higher. Most of the large cloud data center companies, they put their data centers in places where it's more like 3 to 5 cents. So on the right-hand side, what I've shown a pie chart that shows what the total cost of ownership is over a 3-year period, assuming a 10-year depreciation on the capital costs. And there are some other factors about energy costs, et cetera. And what you can see is 38%, or more than one-third of the cost, is related to the energy costs. This green one is the depreciation on the capital to construct the data center for power and cooling. And this purple color is your actually energy consumption cost. I think, did I get that right? Yes, energy usage, so it's based on kilowatt hours. Now this is based on a 3-year life. If you go to a 5-year life and you don't replace your servers every 5 years, the acquisition cost stays the same, and these pieces get even larger. So it's really important to pay attention to energy efficiency. So unless you design your servers for energy efficiency, you're not going to have an impact. And you have to look at efficient average power consumption and not just the maximum power. You want to be able to use all of the power that you paid for. So what did we do with our first server product? I'm proud to say that it's the first 10-nanometer server, but that's sort of just bragging rights. But if it doesn't give you any benefits, it doesn't matter. We have 48 custom ARMv8 cores that run at 2.6 gigahertz. It's got, a fairly large cache, and I won't go into the details of the design. If you're interested, you can go to our website and look at the details of the processor. But if you look at how it compares to a top-end x86, which is the Skylake that I showed you, I've normalized everything to our 48-core processor and compared the performance per watt and the performance per thread. So let's look at how this comparison goes. The top-end Skylake has 28 cores. It sells for a whopping $10,000 price, but it is the highest performance. It's about 18% higher performance than, I think that's how these numbers work out. Let's see, what is the overall performance? It's the yellow. Yes, 18% higher performance than our chip, which runs at 120 watts. On a per-core basis, it's twice the performance, but on a per-thread basis, it's roughly equal. Now, if you look at the performance per watt, there's a huge difference. If you said, well, that's the high end, that's not what I want to look at, let's look at something that is at the same power. So if you take the x86 at 125 watts and compare with this energy-efficient design, now you start seeing that on all of the metrics, this guy starts looking pretty good compared to this x86 at the same power. Once again, if you look at performance per dollar, performance per watt, this one is much better. Then if you go here and you say, what if I was trying to deliver a certain level of performance? How do the two implementations compare? Once again, the energy-efficient design wins out. I'll let you, these slides are on the website, so you can look at them and see what you think. By the way, all of these performance estimates are based on GCC 02. So we talked about overall performance, but average power and idle power also matters, because the energy consumption is not based on what the maximum power is, it's based on the average power. So what we did is we took our chip and measured the average power running the spec-int benchmark. There are 12 subtests in this, on this benchmark. And what happens is when you run these tests, the power is kind of peaky. There's small peak periods when it goes all the way close to the max thermal design point of 120 watts, but most of the time it runs at much lower power consumption. So if you average that across the entire run of these benchmarks, what we found was that the median was 65 watts across all of these tests. So this allows you to do some sophisticated power management to reduce your overall energy costs. And if your servers are idle, the idle power is only 8 watts. So again, this allows you to reduce your energy costs. So you can do things in the design if energy efficiency and energy cost is important to you. But it has to be something that's designed in. It doesn't happen by accident. So with that, let's move on to the next era. So combining with the energy-efficient core, you'll see heterogeneous designs. And there are some things that I've learned from my experience at Qualcomm. Qualcomm does a lot of mobile computing. And energy efficiency is just part of our DNA. When you're designing a processor that fits in a small form factor in a smartphone, your power budget is roughly 2 or 3 watts. So you really have to be very careful. If you look at the desktop PC CPUs, they're not very energy efficient, and I showed you some data that kind of supports that statement. if you have cores that are too wimpy, so if you just take a low-end smartphone core, it's not good enough for servers. So you really have to sort of take that design philosophy and design something that delivers higher performance while maintaining the energy efficiency. But what we also noticed, that on the smartphone, many workloads require something other than just the general purpose CPU. So if you look at smartphones for years, they've had DSPs, they've had GPUs, and different workloads run on different engines because they are best suited for the kind of workload. So you can now do deep learning inference on your smartphone, and that's done using the DSP, for example. So learning from that experience, I think the next wave for servers is also going to be something similar. Heterogeneous accelerators that are paired up with the general purpose CPU. Initially, that will be with attached accelerators attached via the PCIe, but over time, you'll see that integrated into the same silicon as the general purpose CPU. So why are application-specific accelerators important? Well, you can get, at least in theory, an order of magnitude higher efficiency than general purpose computers. Now, the challenge is it does a damn good job on what it's designed for, but it can't do anything else. So this is where the challenge comes in. How do you decide what to put in and how to implement it? Now, this market, the whole AI market is evolving so quickly that the requirements are changing at a rapid pace. So what's important is getting your product done as quickly as possible, because if you're in a typical 3-year cycle like we are in most of the CPU designs, it's very difficult to predict exactly what's important 3 years out. So in order to get your product out sooner, we have to be willing to accept slightly inefficient implementation, not go for the most highly optimized implementation, leave a little bit of power on the table, leave a little bit of performance on the table. There are many, many potential applications. Machine learning gets mentioned the most. There's encryption, data compression, video processing. But the challenge for most of the commercial companies is there needs to be reasonable volume to make the business case. But you can go back in history and see how processors have evolved. I remember back in the old days where there was no floating point. And it started out as a separate chip. And over time, when more and more software started using floating point, now we take it for granted. Now, you can see a similar trend happening in other acceleration technologies. The other important thing is that a lot of the algorithms and the models are changing. So if they're not stable, then it's very difficult to design something that's going to have a long life. So then the question becomes, can we make them sort of at least somewhat programmable so they can adapt to changing requirements? And this is where I think FPGAs fit reasonably well, because they're easy to change. So how did we get to deep neural networks? I mean, in the past, we've talked about AI, and everything was done sort of manually. But there are 3 things that happened about 5 or 6 years ago. There was a lot more data available. There were better models for the data, and very powerful GPUs became available. And that allowed people to look at that data, analyze it, and draw some conclusions. And the real turning point was the ImageNet competition of 2012. And at the end of, there was a paper at NIPS that year. And that started this whole deep learning revolution going on. And now everybody talks about it. And deep neural networks are becoming quite pervasive. So if you look at sort of historically how it's taken off, the chart on the left-hand side shows, again, this came from Google, the number of searches for the term deep learning from 2010 to 2014 and beyond, an exponential growth in the number of people just searching for deep learning. On the right-hand side shows the growing use of deep learning within Google, and they're using deep learning for a variety of different areas, things that you would not have thought about. Why is that? Because of the efficiency So because of this need, they decided to do their own ASIC called the TPU. And what it did was it allowed them to take some of these applications and run them on the TPU instead of burning CPU cycles, which allowed them to deploy fewer servers in their data centers, driving their energy and acquisition costs much lower. So this should not be a surprise to you. Devices and machines are getting more intelligent. You see intelligence at the edge with your smartphone and other devices, and in the servers. So what can we do with this AI technology or machine learning solutions? Well, first you have to observe and see, hear what's going on around you. Then you kind of try and draw some inferences on what does that mean, the thing that you heard, the thing that you read, the pictures that you saw, and then be prepared to take some actions. So AI is happening everywhere. As I said, it's happening at the edge in devices, and it's happening in the cloud and in servers. And often you don't know where the processing gets done. And as we go to 5G and the bandwidth into the cloud increases, then it opens up even new avenues for what we can do with AI. And again, the beauty of the cloud is you have no idea where the computation is being done. You don't know whether it's on your phone or in the cloud, except when your Wi-Fi and your breaks down. So what are some of the silicon alternatives for deep neural networks? At one extreme, you've got CPUs. Often there are plenty of unused cycles, so you might as well use those for machine learning. It's the most flexible, but also the least efficient. At the other extreme, you have purpose-designed ASICs, like the Google TPU, which is highly efficient, but it does only one thing, and it does it extremely well. In the middle, there are a bunch of other solutions. There are GPUs, which are not quite as flexible and efficient, but they do a very good job, especially on the training side of machine learning. And then there's a new era right in the middle, which I call DPUs, or DNN processing units. And there are two flavors. There's sort of the soft DPUs, which are built on top of FPGAs. And I've listed some of the examples. And actually, this slide came from Microsoft, a presentation at Hot Chip, so I can't take any credit for this. And then you also have hard DPUs. There are a lot of startups, and I named a few. Graphcore is here in the UK. Grok is a startup formed by a bunch of people who left Google. They worked on the TPU and then left Google to their own. Intel's doing it. Lots of other companies. So pretty exciting times. Most of these are focused on training, and some of them are for inference. Now, if you look at training versus inference, there are fewer systems being used for training because you train once, whereas inference happens continuously all the time. So the volume on the inference side is much higher. And because the volume is higher, the cost has to be lower and the power has to be lower. So what you see is inference, you tend to go with smaller, more efficient solutions because you want to deploy them at scale in large quantities. On the training side, it's okay to have a power hog GPU or a large DPU, which is 300 watts or higher and costs a couple $1,000s. On the extreme left-hand side, the power budget is probably 50 watts and costs less than $500 typically, or price. So what do I think about the future silicon for deep learning? CPUs are not powerful enough for training, but they have free cycles. So sometimes you'll use them because they're free. But there's an opportunity to add in accelerator cards, which is exactly what Google did when they added the TPU as a PCIe card. And there will be instruction set enhancements that can improve performance for deep learning. In my opinion, GPUs have too much extra baggage. They have too much extra hardware. They weren't designed specifically for machine learning. They do a good job on them. But there's extra die area and extra power for features that are not needed for AI. So scaled-down version of the GPU would work much better. And a lot of the startups have observed this, and they're going with some domain-specific accelerators that are more efficient in terms of area and power than standard GPUs. FPGAs are more flexible, but they're difficult to program and can be expensive. ASICs, as I said, are energy and cost efficient, but less flexible. So lots of things to think about. So if you're in business, you look at the business case, look at your choices, and pick the solution you like best. Neural networks are moving into more than just looking at pictures and telling you whether this is a dog or a cat. They're being used in medical imaging, for example, drug discovery, lots of applications beyond the initial usage that we started to see. In order to do a good job for machine learning, we have an opportunity to dramatically reshape how our computing devices work. For example, I spent a good part of afternoon yesterday in the workshop on approximate computing. In this particular, in machine learning, you don't need the full double precision accuracy that you get with IEEE floating point. A lot of the inference is now being done with 8-bit integers and moving to 8-bit floating point and 16-bit floating point. None of these were thought about as standards. So if you're HPC and you're designing a nuclear reactor, you want that accuracy. But if you're doing some of these other things, close enough is good enough. So you don't need the last bit of accuracy. So this opens up a lot of opportunity for innovation on how do you cost effectively and power effectively design your accelerators to be better than what we have today. So my concluding remarks, single-thread general-purpose performance improvement is slowing down. Energy efficiency is extremely important in data centers. And you heard some of these issues in yesterday's keynote. Even large organizations like ARM have started to, CERN have started to evaluate the ARM architecture because it enables energy-efficient designs at good performance. Typical use efficiency is becoming more important than peak output efficiency in data centers. Idle power matters, and there's an opportunity to do smart power management to dynamically optimize the amount of power you allocate to each of the servers in your data center. And last but not least, there's plenty of opportunity for innovation, both from a research point of view and from a product definition point of view, for application-specific architectures targeted for specific workloads. And I think that's all I have. And I'll be happy to take questions.